let's get started then. So I'm pretty happy. I'm happy to introduce Julie, who I think you all know since she's been the one really running this seminar series. So Julie came from Cornell to join Berkeley Lab in 2014. So she was the 2014 Alvarez Fellow. And she works extensively on optimization algorithms and developing these optimization algorithms such that you can use them in an agnostic way, like in a black box manner for a lot of different scientific applications. And one thing I don't know if this is fully known yet, but unfortunately she's actually leaving Berkeley Lab now to go to NREL, where she'll be taking on an exciting new position working on AI applications and taking some leadership roles there. So I'm excited to hear this talk, and thanks again, Julie, for also hosting this seminar series and putting everything together for it.
Thank you, Aditi. Okay, let's do this. And let's do that. Okay, cool. So I'll be talking about my research along, I don't know, the last 8 years or maybe more, where we do surrogate model-based optimization and we use active learning in optimizing high-performance computing applications. Okay, so optimization, and feel free anywhere in between to just shout out and yell your questions in between. That way I don't have to monitor the chat too much. So optimization problems arise in many different application areas. For example, you may have somebody who contaminates your groundwater and you have to clean it up, but of course you want to clean it up as cheaply as possible. It's shown here on the left side. And then maybe you're interested in cloud simulations. Maybe you have a parameterization of some cloud simulations. There's some values of parameters you can tweak in there to make that more realistic or less realistic. It's again an optimization problem. Other folks are interested in optimizing the parameters in quantum circuits. So you have some optimizer that adjusts some parameters. It goes to a quantum processing unit. You simulate a quantum circuit. You get some energy estimate back. Want to minimize that energy estimate. It's an optimization problem. In cosmology and combustion, we have similar things. We have simulations, for example, of flames or of how the universe expands. You can compare your simulated data with your observed data, and then you want to tweak some parameters in the simulation to minimize the error between simulation and observations. Deep learning has a lot of different optimization problems in it, as well as material science. And there are many, many more that I don't have enough room on this slide to put it here. So optimization problems come in a variety of different flavors. So here's a general optimization problem, the way you write it down. This f of x up here is what I call my objective function. I can have one of them or multiple of them. I can have them with different levels of fidelity. They can be fast to compute. They can be slow to compute. They can be analytic, or they can be given as a black box. And I want to minimize this function f over some parameters x. Those gj of x are just some general constraints. They can be very simple, like simple box constraints, upper and lower bounds. They can be linear or nonlinear constraints. They can be fast to compute or very expensive to compute, or they can be what we call hidden constraints, meaning we don't know that they exist until we try to evaluate our objective function and it fails on us. The parameters down here, this is basically your tuning knobs in your simulation, for example. They can live on a continuous axis. They can be restricted to be integers. They can be both, what we call mixed integer, and they can also be categorical. And then there can be uncertainty in the optimization problem. So that can come in, for example, due to some stochasticity in your simulation. There could be noise in the observations that brings in some sort of stochasticity uncertainty. And uncertainty can either be in the objective function or the constraints or both. So that needs to be taken into account too. And then basically what you have to do if you have an optimization problem, once you write it down, you have to think about what are those problems characteristics, which will then actually tell you what optimization algorithm you should be using to solve your problem. So you cannot just use any optimization problem for algorithm for any problem. So the problems that I focus on is, well, somewhat special in the sense that we can write down again our optimization problem, but we don't actually know what the objective function f of x looks like. So We have some parameters that we stick into a black box, like a simulation model, for example, and out comes a function value. So there's no analytic description of f of x known to us. That means we also don't have gradient information quite often, which is nice in optimization because it tells you the downhill direction where you should be sampling to find the optimal solution. We don't have that. These functions are quite often multimodal, meaning there's several local as well as global optima. So the local optimum is just the best solution in a small vicinity of the parameter. But ideally, you want to find the global optimum, which is the overall best solution over your whole parameter space. And then each of these function evaluations, f of x, is computationally time consuming. So it can take several minutes to several hours to get that function value. That means that during optimization, you don't want to do thousands of function evaluations. And you can also usually not approximate the gradients because gradient approximations need function evaluations, and function evaluations are expensive. So the goal is here to develop optimization algorithms that can deal with these type of problems and find you solutions efficiently and effectively. So one of the approaches that we're using here is called surrogate modeling and active learning. So in a sense, a surrogate model is just a computationally cheap approximation to your expensive to evaluate function. So f of x is my, for example, objective function that I evaluate with my expensive simulation. And s of x is just an approximation of that thing. This s of x is cheap to compute and it's cheap to evaluate. And it helps you make predictions of what f of x may actually look like. And here's a little bit of a cartoon of how the surrogate model-based optimization works. You would start out here in this two-dimensional example with an initial experimental design. You have 4 points where you evaluated the expensive simulation, for example. So you have 4 bits of data input-output pairs. Now you can fit a surrogate model to that. Talk about that, what that could be later. But now you know the surrogate model is exact at these 4 points, but everywhere else, it's the best guess of what the true function f of x looks like across the whole space. So there's by no means a guarantee here that this thing is actually exact anywhere else than at these 4 points. But the idea is now that you use the surrogate model to figure out where in the parameter space you want to do the next function evaluation. So let's say somehow we decide we want to evaluate over here on this right side. We did an expensive function evaluation there. We have now 5 input-output data points. So why not use this 5th point when we update our model? So now at least our model is exact in 5 points. And then during iterative optimization, what you do is you just keep doing the same thing. You use the surrogate model, figure out where you want to do the next expensive function evaluation, like this point over there. You update your surrogate model and so on and so forth. And you keep doing that until you're out of, for example, a computational budget that you set beforehand. Okay, so here's a quick flowchart of what I just described in this cartoon. You need an initial experimental design, some input-output data pairs in order for you, where you do the expensive function evaluations. You have to think about, have you reached your stopping criterion? So let's say, if I say I want to only do a total of 10 expensive function evaluations and I do 10 points in my initial experimental design, well, then your search basically stops there. But usually you choose your initial experimental design smaller than the budget of function evaluations that you allow. So if you don't stop, you create your surrogate model, and then you define what we call an auxiliary optimization problem or an active learning strategy over the surrogate model. And that helps you then to figure out what is the new sample point. You evaluate the new sample point, and then you keep going in circles until you have reached your stopping criterion, after which you return the best solution that you found during the search. But now, I mean, obviously, this is black box global optimization, so there's by no means any guarantee that the solution that you're getting back is a globally optimal solution or even a locally optimal solution. But in reality, in practice, what you find is that the solutions that you find by that is usually better than what you get in practice with what people like to do, like hand tuning, for example. And then in the following, we'll talk a little bit about what these surrogate models could be and what this optimization, auxiliary optimization problem should be. Okay, so what are the surrogate models? So they're radio basis functions. They're quite popular. You can have a very simple analytic description you can write down. You write down its derivative information and can use all of that to help you sampling in your optimization algorithm. You can think about Gaussian process models. They are a little different in the sense that they interpret the objective function value like the realization of a stochastic variable. If you do know that the underlying function looks, for example, quadratic, why not use a polynomial model of a quadratic shape, right? All the information that you have, you should exploit. Or if you happen to find yourself in a large data setting with many input-output data points, then deep learning models can come in as good models that predict input-output relationships for you. But again, the surrogate model that you choose here should depend to some extent on the problem, optimization problem characteristics that you're dealing with. So then I talked about somehow we use the surrogate model to select a new point where we do the next function evaluation. So here are two examples how you could do that. Gaussian process models, what we like to do is maximizing expected improvement. So here in this top panel, you see a one-dimensional function, f of x, function of x. This red curve is the function you want to learn. The red dots are the observations where you have basically evaluated f of x already. The blue curve is your Gaussian process model approximation to the data. And this blue envelope is the uncertainty that's associated with the predicted function value. And now what you do is you take basically the prediction and this confidence interval here and bake it in what we call an expected improvement function that's shown in the bottom panel. So this expected improvement is going to be 0 at all those points where you already done a function evaluation, because you know the function value, there's no uncertainty. You don't expect there to be any improvement if you sample there again. Everywhere else, this thing is larger or equal to 0. And the idea is to sample at the point that maximizes the expected improvement, basically that in some sense that maximizes that the next point will improve on the best point you have found so far. So this is how we sample with Gaussian process models. The regular basis functions are a little bit different. They do not give you this uncertainty estimate with their predictions. So we have to come up with a different sampling strategy. So here's a two-dimensional example. These black dots are where I've already evaluated my expensive function. So is this red dot. The contours are my radial basis function approximation of the underlying function. And the way that I sample with radial basis functions is that I compute what I call a score. I go to the best point I've evaluated so far, like this red dot. And then I add random perturbations to this red dot and I create a cloud of candidate points. And then out of these candidate points, I would choose one or multiple of them that minimize a score that's computed based on the distance of the candidate point to already evaluated points, as well as the RBF, radial basis function, predicted function value. So in that sense, you can use radial basis functions for sampling. And you can come up with your own sampling strategies as well. So Gaussian process models work well when you have smaller dimensional problems with few sample points. And they work pretty well when you have noisy objective functions as well. One of the drawbacks of Gaussian process models is that when you compute the hyperparameters of the Gaussian process model, it requires maximum likelihood estimation that involves some Cholesky factorization that, as the number of samples becomes large, means that computing the Gaussian process model itself becomes computationally more involved. The expected improvement that's shown on the bottom panel here becomes increasingly multimodal. So every time you want to sample using expected improvement, you're solving again a global optimization problem, and you don't generally know or you get the global optimum or not. The radial basis functions, they work well when you have large dimensions and large number of samples, and they're computationally quicker to compute than the Gaussian process models, but off the shelf, they don't work so well for noisy functions. So you have some advantages and disadvantages of each here. And again, your optimization problem should basically dictate for you which type of surrogate model and active learning strategy you should be using. And then again, this is not, by all means, this is not the only way that you can sample using surrogate models. Depending on what your problems, characteristics are, you have to tweak those things, or you can develop your own sampling methods as well. In the following, I'll just talk a bit about different application problems where we use these surrogate model-based optimization methods. And the first one is where we looked at cloud simulations.
General question before you do that?
Yep.
So you have these here in 1D and 2D, right?
How do I go back? Yes.
What if I have like, 500 parameters? Like, do you do the same sorts of things? Do you do different things?
I want to caution with 500 parameters. That's pretty large dimensional. Like surrogate models will use 100, 200 parameters. I think some people push the radial basis functions to 500 parameters, but the more parameters you have, the larger an initial experimental design you need. So the radial basis functions, you need at least dimension +1 to get started. So 500 parameters means 501 initial samples, which is already a load.
No, but like, suppose I have that, right? Suppose I can do 1,000 samples, right? Like, do you still follow these sorts of things, or do you start to think about other methods that you would want to use?
I would still think about these sort of things to some extent. Depends on how expensive your function is. If it's like really expensive, then this is sort of like your only viable opportunity. With Alejandra, we're working on some ideas on dimension reduction. Like try to figure out which ones of those 500 parameters are the most important before you do any sort of surrogate modeling.
Yeah. Okay, great. Thanks.
Thank you. All right. So yeah, I should have asked. So yep, cloud simulations. So here we work with Wolfgang together. He is an expert in simulating clouds. And we do know that a simulation of clouds is a source of high uncertainty in global climate models as well. And what we basically tried to do here is he had this single column parameterization of these clouds where he had some tuning knobs on there that he tried to adjust such that the parameterization's output data comes close to what he had in terms of benchmark data from LES simulations. So after some back and forth, we realized this is a simple optimization problem where we have an objective function f of x, that's this error between the parameterization and the LES data. We only have 6 parameters that live on a continuous scale, and they're all constrained by upper and lower bounds. So this is an optimization problem in this purple box. This is probably as easy as it gets. State of the art is for solving these type of problems, at least in his area, is that people would do a parameter sweep or a grid search. So like illustrated in this 3D cube down here, where you go into each dimension of your problem, you divide it into little intervals, you get this kind of grid, and you evaluate your objective function at each grid point. Now, that does not really scale well with the dimension. And what it also does is it oversamples areas in the parameter space where you really don't care about what's going on because the model is so far from the data that you don't want to sample there a whole lot. And the other thing it does is that it undersamples interesting areas. So maybe in some corner you have really good model performance, but this thing kind of like off the shelf does not just allow you to zoom in there a little bit more and do more of a local search for more improvements. So what we did here is we used simply our radial basis function surrogate model algorithm I just described on this problem, and then we looked at, can we actually find any good results? And on this right side, you can see 2 images. And basically what you see is there's a black curve in there in each image. That's your LES data. That's the data you want to match as closely as possible. The green curve is what you get with default parameters used in the parameterization. So you can see it fits pretty okay, but it's not perfect. And then red and blue are 2 solutions that we find by using 2 different types of surrogate modeling optimization approaches. And now you can see that both red and blue are almost identical to this black curve. So we can find significant improvement over these default values that were used before. So this was pretty cool. This was just sort of like a side quest of collaboration there. And then a very different application comes in high energy physics event generators. So there are these physicists like Steve and Shangyang and Holger, and they like to look at what happens when particles collide, and there's observation data of these events when particles collide, but they can also simulate that on a computer. And now the question is, again, in a simulation, you have tuning knobs you can adjust, and then either as illustrated on this left side, so we look at these type of histograms that you get out of your event generation. Basically what you want is that the measurement data, the black data, what you observed, is as close as possible to the simulation data, or like the other way around. Simulation should be as close as possible to the measurement data. And to get the simulation data closer to the measurement data, you tune these knobs. And normally we don't look at a single one of these histograms. We look at hundreds of these histograms. And the current practice is that you tune the simulation parameters by hand and use some sort of an eyeball metric, where maybe Steve and Xiangyang look at the same distribution here. Steve says, yeah, this looks quite acceptable. And Xiangyang would say, no, I really don't like that fit. So there's already this like physicist bias in there as well. So one of the things that we did here in this project is we formulated an optimization problem, and we developed some what we call objective comparison metrics. So we get this eyeball metric out of there. And this is a very large dimensional problem. I think we had over 100 parameters W that we tried to optimize here. And we have an equality constraint in there as well, but that one was very, very easy to take into account. And then we applied our surrogate modeling optimizer, and we found really good solutions, really good fits, and really good optimal parameters for the simulation that was better than what the physicists were previously using. And Holger here, a collaborator who's now in England, he used that optimizer, called it Apprentice, and put it into his high energy physics optimization toolbox, and he's still using it. So this is a pretty cool success story of how automated optimization can help you also in high energy physics applications. And then currently we're working with Wim on optimizing noisy intermediate scale quantum devices. Now, I'm obviously not the expert in this application, but the goal is here that we want to optimize some parameters theta in a quantum circuit. And you kind of like go back and forth between a classical optimizer that runs on your average machine. It generates some parameters, and then you do a quantum circuit simulation, and it gives you back an energy estimate of some Hamiltonian that you might be interested. And your goal is to minimize this energy estimate. Again, the optimization problem is pretty easy to write down, in the sense that we want to minimize an expected energy over some parameters that are just in a box. But one of the problems here is that the objective function, our E, our energy, is kind of like noisy. So for the same parameters, I evaluate that thing twice, I get two different solutions out of it. So that needs to be taken into account when you do your surrogate modeling. So here what we used is Gaussian process models. We only had, I think the biggest case we looked at had 21 parameters. And we use Gaussian process models to approximate this energy. And we use a combination of two optimizers here. One is Gaussian process model with expected improvement sampling to figure out a little bit the global lay of the land of the objective function. And then starting from the best solutions we found with the Gaussian process model, we used the local search from there to refine basically the most promising points. And on the right side, you can see a performance comparison between what's state of the art. So implicit filtering is this yellow thing here, is what is currently mostly used for getting good solutions for these type of optimization problems. The goal here is to have your curve go as low as possible, as quickly as possible. And you also want to have these envelopes very skinny. So here, these envelopes is basically just a standard deviation computed over 3 trials with the algorithm. And now you can see that the state of the art, the implicit filtering in yellow, it makes a lot of progress. It has large performance variability, but it is significantly slower in terms of convergence than anything that we used with our Gaussian process models, which is illustrated in red and blue. So again, this is another example where, surrogate models can help you find better solutions quicker. And now I want to switch gears a little bit and talk about multi-objective optimization. I think that's a fun topic to talk about anyway. So in multi-objective optimization, we don't only have one objective function to minimize, we have multiple. And those objective functions are conflicting, meaning that as you improve one objective function, another one gets worse. And basically what that means is that there is not a single solution that optimizes all of your objective functions at the same time, but what we're looking for are a set of trade-off solutions or Pareto optimal solutions. And I tried to illustrate that down here. So in this example, we have 2 objective functions, f1 and f2, and we want to minimize both. So basically, if we were able to find one point that minimizes both functions, we would end up in this lower left corner here. But usually that does not exist. So what we're looking for is what's illustrated in these dark blue squares, which are our trade-off solutions. And a trade-off solution here, an example is point A and point B. And now you can see here in the illustration that point B has a better function value in terms of criterion F1 than A has, but A is better than B in terms of criterion F2. So in one it's better and the other one is worse. So in a sense, these two solutions are not comparable. Those are trade-off solutions. And this is what we're interested in getting out of multi-objective optimization. On the other hand, if you look at this point C, you can see that it's what we call, it's a dominated point, because C does worse than point B in terms of both criterion F2 and F1. And it also does worse than A, of course. So C would not be a solution to the problem. The only solutions to the problem are the ones in the dark blue squares, as well as point A and point B here. And that's what we're trying to get out. Just to give you a practical example, if you think about airfoil shape optimization for some reason, your goal might be to minimize the drag and to maximize the lift by adjusting the shape of that airfoil. Now, generally what happens if you adjust the shape, you improve the drag, but you make the lift worse and vice versa. And that's what we call multi-objective optimization. Now, you have to think about how can we solve that? So we know objective functions are expensive to evaluate. And the way I talked about the sampling, it doesn't really fit into the multi-objective ideas here. So what we can do here is we can use separate surrogate models for each of our expensive to evaluate functions. So let's say F1 and F2 were evaluated each at these circles and these diamonds. I can just fit two separate surrogate models and I work with that. So it's pretty easy to do. And now how do I sample? So we have these two different surrogate models. Now we can think about the two spaces that we can look at and use information from. So in multi-objective optimization, we have on the one hand the decision space and the objective space. So here's a two-dimensional example, and we have two objective functions. So the decision space, we have a point. Let's say we select point number 4 over here. We evaluate both the objective function F1 and F2, and then we can plot that point into the objective space, which, because we have two objective functions, is also two-dimensional. So each point in the decision space corresponds to one point in the objective space. Some of these points in the decision space lie on the Pareto front, and other points, like point number 2, is dominated by other points. But now we have these two spaces. We can use the information from both to define some sampling decisions. So here we developed a variety of different sampling methods. Here's where we first look at the objective space. So we want to minimize objective F1 and F2. Ideally, a good Pareto front has points that are fairly equally spaced out across the Pareto front. So in a sense, if you have a single point up there, and you have a massive gap until you get to the next Pareto optimal solution, that's usually not good. So what we could do is we can say, okay, find a point that maximizes the distance to neighboring Pareto optimal solutions. That will basically give you two target values. So here for F1, you wanted this point to be function value 2. For F2, that function value should be 20. And then you can simply define, because you can do whatever you want in sampling, you can come up with an auxiliary optimization problem where you try to find a point X for which F1 of X is 2 and F2 of X is 20. And then you can use your surrogate models by minimizing this computationally cheap multi-objective problem to find either one new solution, if there exists such a solution, or multiple new solutions, X, at which you evaluate your expensive functions, and then hopefully you improve your Pareto front. And then we can also look in the decision space. So let's say we do know at any stage of the algorithm, we do know which ones are the current Pareto optimal solutions, non-dominated solutions here. And you can go to those points, add random small perturbations to it, and make predictions with your surrogate models of what the function values should be. And if any of these perturbed points are predicted to be non-dominated, I would evaluate the expensive functions with that in the hope to locally improve my Pareto front. Sometimes you're interested in how good or how bad can each one of your objective functions become. So let's say I was interested in how small can F1 be if F2 did not actually exist. So you can just minimize objective F1 separately. The way you can do it, again, you just look at your surrogate model, find the minimum of it, and evaluate there, and then you can, hopefully you find an extreme point of your your objective function of your Pareto front. And you can do that for F2 as well. So there's all these different sampling methods that you can use. Some of them are local, some of them are global, but combined, they give you a pretty good method for finding Pareto optimal solutions. And here's a two-dimensional example where we applied that. We have objective F1 on the left and F2 on the right. And you can see if we go from the optimal solution of F1, like forwards in the screen, towards the optimal solution of F2, you can see that the function value for F1 gets worse because you walk away from the minimum, but the function value for F2 gets better because you walk towards the minimum. So these are two conflicting objective functions here. And now here's an illustration of what the sampling looks like in the objective space. This is our initial experimental design. I found 2 points that were non-dominated. So clearly X is dominated because these two ones with those red circles are better in both criteria. But now as I keep sampling with these 3 different methods that I just briefly described, you can see how your sample points start to evolve towards the lower left corner. So we found some new points. The previously non-dominated points are now dominated, so we forget about them. And then we keep sampling along. And you can see how this Pareto front is starting to take on its true shape there. So as you keep sampling, you fill it in and you locally improve it. Some solutions that were Pareto optimal in a previous iteration are no longer, they are now dominated, but eventually you find a pretty good filling of this Pareto front. And this is the result that you want to then give back to the person who asked you to solve this multi-objective optimization problem for them. Okay, and now current state of the art for doing multi-objective optimization is to use genetic algorithms. I am realizing that this should be a 1 dimension up here, not 2 dimensions. So just to give you an idea of why genetic algorithms might not be the greatest choice for solving multi-objective problems is shown in these 2 illustrations. So on the left side, I have a optimization problem of a single variable, and I have 2 objective functions. And I know that my Pareto front is nice and connected because, well, I wrote this thing down analytically. I just wanted to compare how those things perform. And now you can see on these histograms where over the parameter space, the surrogate model algorithm sampled, and where the genetic algorithm sampled. And you can see that the surrogate modeling algorithm, it searches globally, like it samples everywhere across the space, but then it focuses most of its samples right here in the middle. And this middle point basically corresponds to the Pareto optimal solutions. The genetic algorithm, on the other hand, focuses all of its samples on this middle part here, which again corresponds to the Pareto optimal solutions, but it does no global search at all. And in this lower figure, in our lowest panel, you can see in red is what the surrogate model algorithm gives you for Pareto optimal solutions, and green is what the genetic algorithm gives you. And now you can see they look very similar, but you can see that the red curve is a little bit better filled in this tail end on the right side, where the genetic algorithm has a bunch of holes in it. So in a sense, the surrogate modeling algorithm finds you more Pareto optimal solutions than the genetic algorithm does. But then the main difference between those 2 approaches, you can see on the right side. It's a very similar problem. We have 1 dimension, 1 parameter we want to optimize, and 2 objective functions. But in this example, the Pareto front is disconnected. And now what you can see here, where the surrogate modeling algorithm sampled, again, it searched globally, and then it found sort of like 2 areas where it focused most of its sampling on. The genetic algorithm, on the other hand, only focused its whole sampling on 1 area. And what that means for the Pareto front is shown on this lowest panel here. You can see in green again is the genetic algorithm. It finds what it thinks is a simply connected Pareto front. And it sort of like misses this whole part of this disconnected piece of the Pareto front. So the surrogate modeling algorithm found out by its sampling that you can see in this bimodal distribution almost, found out that there's a disconnected Pareto front here, and it samples it very well. And the genetic algorithm, if you were to only do that and you trusted its result, it gives you basically back a bunch of solutions over here that are in reality not even Pareto optimal solutions, because in fact, they are all dominated by solutions that are down here. But the genetic algorithm never sampled over there, so it never found that. So that's pretty cool. So this is how you can use surrogate modeling for solving multi-objective optimization problems. Okay, and then with my last couple of minutes that I have left here, I want to talk about how we can solve integer constrained optimization problems. So integers meaning that some or all of your parameters have to be numbered like 1, 2, 3, 4, 5. We use radial basis function models here because they seem to be performing off the shelf way better than Gaussian process models for these tasks. And you have applications where you have integer optimization in many different areas. So this could be in structural optimization, in reliability, redundancy optimization. It could be in architecture tuning of deep learning models. There's a bunch of integers there. And basically what we can do is that we simply go to our same type of sampling methods as before with our radial basis function, but we apply some tweaks to it. So just to recap, here's a two-dimensional example. Black points and this red dot is where we evaluated the true function. Now you have to see that parameter 1 we say has to be integers, parameter 2 can be a continuous. So you can see that already by definition, how we sampled the initial experimental design, we made sure that parameter 1 is only sampled at integer increments, whereas parameter 2 can be basically everywhere. So the contours is my radial basis function approximation of the true underlying function. And now I want to create these candidate points again by perturbation. But now I would go to my best sample point that I found so far. And I would, previously we just added random perturbations to it and we created this cloud around this best point found so far. But now we have these integer constraints. So a simple tweak that you can do is that for the integer parameters, you just add integer valued perturbations to the best point found so far. So that's, and for the parameter 2 that's continuous here, you can add any type of perturbation to it. And that's how you would basically end up with what looks like these 4 columns of candidate points. So these candidate points by generation satisfy the integer constraints. And now if I choose one or multiple of these candidate points as new sample point, that candidate point automatically satisfies the integer constraints and life is good, basically. And then, yeah, we can still show convergence, even though it's a convergence only in probability, meaning if you sample for forever, you'll find your global optimum. Not very useful in practice, but at least, you know, it means that I'm never going to sample the same point more than once. So that's pretty cool. It's pretty easy to do, just going from your continuous sampling to an integer constraint sampling. Now, what kind of applications do we have here with integer constraints? One of them comes in nanomaterial development. Nanomaterials you need, for example, in desalination membranes, you need them in photovoltaic cells, maybe in the textile industry if you want to have a cool water resistant repellent, I don't know what the right word is, t-shirt. But one of the problems with nanomaterials is that manufacturing introduces a bunch of defects. So defects basically determine the performance of your material. And so there's an application where we worked on with a bunch of people from the ALS and the material science and chemical science divisions. And we tried to basically look at a nanomaterial. Here's a very simple example. We look at these multiple layers that are in this nanomaterial. And one of the questions in manufacturing, you make this thing, one of the questions that comes up is how thick is each one of these layers of different materials? And how thick are these layers where 2 different materials basically touch? So one of the ways that you can find out these different thicknesses or what the performance of this material is that you do what's called X-ray standing wave experiments. So you take that sample and your friends from the ALS look at it and they do their thing with it. I'm not an expert in that area, but what they get out of their experiments is basically these different points over here in this middle figure. So they get these dots out of it. And now I want to find out what are the thicknesses of each layers so that with a simulation, I can recreate what these dots are. So I would basically look at adjusting some thicknesses of these layers. I run a simulation with those thicknesses and I get out, well, we call them rocking curves, these different rocking curves for the different materials. And ideally, these solid lines agree as well as possible with the data. The current method, the way Slavo and everybody used to be doing it is they used an Excel spreadsheet. Somebody sat there, put some thickness numbers into it. They clicked a button, wait for the simulation to come back, look at the results, don't like it, and then somebody updates these thicknesses. So this is really slow again, and in large dimensions, it's pretty difficult to do for a human being, I think. So what we did is we developed a optimization problem that had integer constraints. We used integer constraints here because, as I learned, apparently if you have layer thicknesses that have a difference of 0.2 angstrom or less, you can't really distinguish anymore. So why not just formulate this thing as an integer constraint problem? Because now instead of searching over a continuous and infinite number of solutions, I can only search over a limited number of solutions. And we also know how to do integer optimization. So that was a pretty cool, clear application. And our surrogate model optimizer that I just described in the previous slide found really good results for that. And it's definitely quicker than any scientist sitting there doing that by trial and error. And this was then implemented in, I think it was called swapped software that Matthias put together, and Slavo is still using that at the ALS now for his standing wave experiments. So that was another cool application area that just was sort of like a side quest that just randomly came along at Berkeley Lab, where we could, in some sense, throw a surrogate model optimizer over the fence, and it worked really well. And now in the end, I want to talk briefly about deep learning architecture tuning. That's what we're currently working on a fair bit. So deep learning models are a lot used throughout different science areas now. One of the questions that comes up when you try to use deep learning is, well, what model architecture are you going to use? So an architecture here is defined as by hyperparameters, such as the number of layers, number of nodes, the batch size, dropout rate, and so on and so forth. And these hyperparameters, this architecture defines how well your model can actually perform for the task. If you write it down mathematically, it's a bi-level optimization problem as shown in this lower left corner here. So what you basically do, you want to minimize some sort of an objective function u that depends on your hyperparameters theta and some other parameters. Now, in order to figure out what is this performance u for your hyperparameters, you fix them, gives you an architecture, and then you train the model. Training a model is basically solving a lower level or a nested optimization problem that's shown in this blue box. So for each set of hyperparameters, you fix them, you train it. Training means you optimize over weights and biases. And once you have the solution, you hand that back to the upper level. And now finally, you can evaluate what the performance of those hyperparameters is. You don't like the performance of those hyperparameters, you adjust them, you solve this lower level problem, the training problem again, and you get a new function value out of it. So in some sense, you can interpret that as a black box optimization problem where I want to minimize the function u over theta, kind of like ignoring that this whole training is another optimization problem at the lower level. So that's how we look at it. And then we can fit a surrogate model that maps the theta space, the hyperparameter space, to the performance of those hyperparameters. And then it'll help us figure out which hyperparameters to try in each of these optimization iterations. One of the things you have to think about when you use deep learning models is something like a variability that can come in. So basically, when you do the training, this lower level solution here, you use something like stochastic gradient descent or some other method that has some stochasticity in it, meaning that if I use the same architecture, illustrated down here, the same architecture, and I train it 3 different times, and I make 3 different predictions out of it. Those predictions can be very much different. So why is that? Because every time you train this thing, you have a different random number seed. Stochastic gradient descent gives you a different model basically out of it, and each different model gives you a different prediction. Now, ideally, I would like to have a model, an architecture that has a very low variability. So when I use it for making predictions, I know that with some 95% confidence, I will fall into some upper and lower bound of where I need to be. And that is currently by hyperparameter optimization methods not done. They sort of like sweep the stochasticity under the rug a little bit, which may be a problem if you want to reproduce, for example, scientific results you found in a paper somewhere. So one of the things you can do to assess this prediction variability is simply by sampling-based methods. A fully Bayesian method is not gonna be computationally efficient enough. So one of the things you can do is what I just described, you train the architecture multiple times, you get multiple predictions out of it. You can compute some statistics like expected performance and the variability of the performance, and then use those values for selecting the next set of hyperparameters you want to play with. Another thing you could do is monte-Carlo dropout, where you train your model, and then you use a dropout mask at prediction time, meaning with some probability that's larger than 0, some of the neurons will not contribute to the prediction of the model. And you can apply many different dropout masks, you get many different predictions, and then just as before, you can compute statistics, sample averages, performance, and variance metrics, and then use that as your performance metric of your hyperparameters. Cool. And now this seems to be computationally quite expensive because there's a lot of training here and a lot of predicting. But Vincent, my postdoc, has been implementing this algorithm into a software, Hippo, that you can find on the internet, and you can get it through pip as well. And it allows you to optimize the architectures of different types of machine learning models, and it makes use of nested asynchronous parallelism, so that when you do the sampling to assess the variability, this stuff goes in parallel, and it's like significantly faster than if you did it all sequentially, of course. And you can use it pretty easily with your own data and your own models. There's a software, there's a website with that has a really good documentation you can look at and different examples you can play with. Cool. And then last summer, we applied this Hippo software, or whatever state it was in last summer, to 3D image reconstruction. So that was a big project with a bunch of summer students together. And what you do here is you have a bunch of 2D sinograms. You stick them into a reconstruction algorithm to get a 3D reconstructed tomogram out of it. Now, that reconstruction algorithm is computationally not cheap. So one idea is, can you replace it with a deep learning model? And here we used the UNet to try that out. And here's just a bit of a result, what we found. So the left side is our reference reconstruction, is what you get from the full reconstruction algorithm. The middle is what you get out from your deep learning model as a reconstruction. And the right side is the difference between the truth and the machine learning model reconstruction. And you can see that this, so dark is good. So you can see that there's pretty good agreement between the true reconstruction algorithm output as well as the machine learning model output. So that's pretty nice. And now currently we're also we're currently working on using Hippo for high energy physics applications, again with Xiangyang together. And the goal is here that we have a parametrization and a hadronization simulation that's computationally very expensive to run. And the question is, can we at some point perhaps replace it with, again, a generative adversarial network? So currently what we're doing is we use data generated from this parametrization to train a GAN on it. And then we optimize the hyperparameters of that GAN with the goal to minimize the Wasserstein distance. Wasserstein distance basically measures what is the difference between the ground truth distribution that we have here in blue and the generated distribution, with the goal to make the generated distribution as close as possible to the ground truth. And we've been working on that for a bit. These are just some preliminary, not the most recent results, and it's going pretty well. So again, hyperparameter optimization using surrogate modeling for integer constraints works, has been shown, works pretty well on already 2 very different applications here. And with that, I'll leave it here and I'll open it for any questions that might be there.
Great. Thanks a lot, Julie, for a great talk. I think Lex has a question.
Thank you. That was really great. So for somebody who is an expert in using, well, any of these things, right? Is there like a thing we can pull off the shelf to start thinking about, to start playing with, or this is really something that requires, you or one of your postdocs or somebody that's an expert in the field that can try and make use of this?
Of the Hippo software or the surrogate modeling in general?
The surrogate models.
I want to say, I mean, I want to stay employed, right? So of course you need me. No, so what I've done in the past is like I just make the algorithms available and try to like write some sort of a documentation with it. I do know people use it because it's you know, like people would reach out and like, oh, I have a problem here with this and that. Or other people just use it in computational comparisons to their own developments. So for a lot of this, there is some code online on our like optimization.lbl.gov site or something like that. There's also just to get started with surrogate modeling, Python scikit-learn has Gaussian process models implemented in it. It's pretty easy to use off the shelf. Is maybe not the most efficient implementation, but you know, to get started.
Mhm.
And there's actually more and more coming up too. Like there's something called GPyTorch that is also a Gaussian process model thing that uses GPUs to make the Gaussian process models more efficient. Also has a really good documentation with it. So yeah, there's stuff out there. But I think the crux is always if you have an optimization problem, like what do you even look for if you're not an optimizer, right?
Yeah, no, that makes sense. Okay, thanks.
Yeah, thank you.